Hi guys, Mr. Yusten here. And today I want to talk to you about electron configurations and how you can do sort of a shorthand for it. So we have the element sodium here. Now sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. It ends with a third energy level, s orbital, 1 electron. Magnesium, the one right next to it, is 1s2, 2s2, 2p6, 3s2. So the only difference between sodium and magnesium really is this 3s1 and the 3s2. There's a whole section here which is really repetitive. Okay, 1s2, 2s2, 2p6. It appears in both of them. In fact, it'll actually appear in every element after sodium and magnesium. Everything higher than 11 and 12 will have this section in it. So this got really repetitive, so a long time ago scientists decided we're going to kind of do a shorthand for this. They noticed that the noble gases over here on the right of the periodic table, those are the ones that basically have full valence electrons. So this family of elements here, the noble gases, we decided that these would be the shorthands, and we will replace a section of the electron configuration with basically the symbol for one of these noble gases. So this repetitive part, 1s2, 2s2, 2p6 right here, I'm going to replace it with one of the noble gases, neon, and then do the unique part about sodium, the 3s1. So instead of writing the whole electron configuration, I'm going to write neon and then continue the electron configuration from that point, 3s1. For magnesium, I'm going to do the same thing. I'm going to take this repetitive part, I'm going to replace it with the element neon, and then I'm going to say continuing from neon's electron configuration, 3s2. So this is just sort of a shorthand way of writing noble gas configuration. So let me give you one more example. So I'm going to do the element bromine. Okay. Now bromine appears on the periodic table right here. All right. It is number 35, 35 electrons. So if I were to write the electron configuration for bromine, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 5. Okay, so 4p5 is how it ends. Now, to do the shorthand version, what I'm going to do is I'm going to go to and basically replace most of that with argon. Okay, the reason why I'm going to do argon is because that's the noble gas that comes directly before bromine. The row above it, the end of that row. I can't do krypton because that's actually after. That's more electrons. I can't do neon because, well, it's too far away. I want to use argon here, and then I'm going to continue it from that point. So I'm going to start with argon is my starting point, and then after argon, argon ends on 3p6, so the next section would be right over here with potassium, 4s2. Then we go down here into the D section, so that's 3d10. And then we do the final bit for bromine. 1, 2, 3, 4, 5, and the 4p. 4p5. And that is the noble gas configuration for bromine. A lot shorter. So the last thing I want to teach you guys today is something called valence electrons. Now, valence electrons are the electrons on the outermost energy level of the atom. So in this case, for sodium, they would be everything in the 3 energy level. So sodium has 1 valence electron. It's 3s1. Magnesium, its valence electrons also in the 3 energy level, whatever the outermost energy level is, 3s2. So valence electrons are electrons that occupy the atom's outermost orbitals, which are always going to be s and p. You're never going to get a d that's the outermost because those always fill in 1 below, or an f because those always fill in 2 below. These are the electrons that are associated with the atom's highest principal quantum number, their highest energy level. Everything in that high energy level. All the other electrons are called kernel electrons. Kernel electrons are ones that occupy the inner orbitals. They're all non-valent ones, basically. So let's do a few examples here. Let's start off with nitrogen. All right, nitrogen has an electron configuration of 1s2, 2s2, 2p3. Now, the valence electrons are all of the ones that are in the outermost energy level. So the valence electrons would be these ones right here in the second energy level. So 2 plus 3, 5 valence electrons. Okay. Now let's try sulfur. Sulfur is located right here. And sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Okay? Valence electrons are the one located in the outermost energy level, which for sulfur isn't 2, it's 3. So it is 3s2, 3p4, so that means it has 6 valence electrons. So this time let's try selenium. Okay, so selenium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Okay? So that gets us to selenium. Now, it's only the electrons in the outermost energy level, which in this case is the 4th energy level. So there's a D in between here, but it's 2 plus 4, 6 electrons. Okay? One last bit of information here. I'm going to go back to my first few examples. Nitrogen had 5 valence electrons, and it is in the 1, 2, 3, 4, 5th column. Sulfur has 6 valence electrons, and it's in the 1, 2, 3, 4, 5, 6 column. And then selenium is also in the 6th column, and it also has 6 valence electrons. So you can actually just count by column how many valence electrons it has. 1, 2, 3, 4, 5, 6, 7, and then everything in the noble gases would have 8. Everything in the D section and in the F section would basically just be filling in lower kernel electrons, not valence electrons. So everything in here would have the same thing as this column right here, 2 valence electrons. Now here's why we need to know how many valence electrons something has. We can actually make a basic Bohr model just showing the outer energy level of the atom. So this is a visual representation of the atom's electrons, but only the outermost energy level. So here's the Bohr model for sulfur. It's got 16 protons and 16 electrons. So 2 electrons in the first energy level, 8 electrons in the second energy level, and then 6 electrons in the third energy level. So the electron configuration for sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, now this has 6 valence electrons, which you can see that if you count how many are in the outer energy level here. So a Lewis dot diagram is basically just a short version of this that's skipping all the kernel electrons and skipping all this other information. It's just showing the valence electrons. All right, so I have the symbol for sulfur, and then I have got 1, 2, 3, 4, 5, 6 dots around it showing the 6 valence electrons. So first thing you need to do is you write down the symbol for that element. In this case, I'm doing a generic X to represent that symbol. And then you start writing dots for each of the valence electrons. You're going to start up at the top, and you're going to write a dot for the S1 electron, and then another dot up at the top for the S2 electron. So the top of the symbol represents the S electrons. Then the 3 sides around it, left, bottom, and right, represent the P electrons. So you're going to do a P1, and then a P2, and a P3, and all of those go on different sides because they're not paired up. They're going to go up, 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 just like the orbital pair diagram. They're separated first. Then you actually start adding in, once you get a 4th one, pairs up with one of the other P's. So you get a P that pairs up on the right, and then a P that pairs up on the bottom, and then a P that pairs up on the left, and then you have all 8 valence electrons. Valence electrons are full. That's as many valence electrons as you can have. So let's do another example here. Okay, so I've got aluminum, which is 1s2, 2s2, 2p6, 3s2, 3p1. So really it's got 3 valence electrons. Okay, so I'm going to write the symbol for aluminum, and then I'm going to do a dot for one of the s's, and then another dot for the other s up top. S's are always up top. And then I'm going to do a P off to one of the sides, and that's it. 3 valence electrons. Now let's try an example for bromine. Okay, so the element bromine. Now I'm not going to give you the electron configuration this time. All I'm going to do is look at the periodic table, and bromine is right here. It's in the 7th column, so it has 7 valence electrons. All we're doing is the outer energy level, so just drawing those 7. So I'm going to write the symbol for bromine, and you always have 2 s's first, so you're going to have 1 and then 2 s's, and then we start doing our p's. So we have 1p, 2p, and 3p, and I'm putting them on the 3 sides. And then I'm going to start doubling up after that, 4p, 5p, and that right there is 7 valence electrons. So that is the Lewis dot structure for bromine.